So, what we're going to do for lab today is a little more about the respiratory system. Um, we're going to be looking at spirometry, which is measuring the volumes of air that kind of come in and out of your lungs as you're breathing, as well as the flow, like the liters per second. And these are really useful from a clinical standpoint, trying to assess respiratory function and all that. So I'm going to start with a little background information on it, and then we'll get into the actual lab itself. So spirometry. There are lots of ways to measure the amount of air, the volume of air coming in and out of your mouth. There's wet spirometers, dry spirometers, this and that. When we're in actual lab, we usually show different ways. There's basically you can blow into this thing with a little dial on there that tells you how much air did you blow out. Like how much was it? 1 liter, 5 liters. That would be like a dry spirometer. Wet spirometers actually, from their name, use water, which would be more like this. There's usually like a bell kind of floating in some water. And then instead of this deal, you kind of have a hose that goes under here, and as you blow air in or out, you can just watch this thing float up higher or float down lower. So a wet spirometer just uses a system like this. Basically, as the air fills this bell here, it'll float up higher or lower, and you can just measure from a little scale again, like what the volume of air is. The thing that we use in our lab is something that's different from all of this even, which I will show you in a few moments, because it involves flow. It's actually measuring the flow. Instead of just measuring the volume, it's measuring the liters per second that are coming out. So I'll get there. So let's start with volumes. So liters of air, and the convention is as things get more positive, that means that you're blowing air out. As they become more negative, you are, I should take that back. As they become more positive, there's a larger volume of air in your lungs. So the sign is important. So if I have the volume going like up and down, up and down, this would be I'm breathing in. As it's getting less, this is breathing out. Right. So as this gets lower, that means there's less air left in my lungs overall. As this is getting more liters here, that means there's more air that I've sucked down into my lungs. If you're just doing quiet breathing, just like quiet breathing is also called tidal breathing. So if I have just my breath going up and down like this, maybe Give it a color. This volume of, like, I've exhaled, I'm inhaling, exhale, inhale. If it's quiet breathing, it's also called tidal breathing. Tidal, because you think of like the tides ebb and flow, right? If you're just sitting there, the air is kind of coming in, coming out. Like you're not even thinking about it, right? You can do more of these voluntary things like, but if you're not thinking about it, the air is still just flowing in, flowing out. That is tidal breathing. And V sub T, this tidal volume, is typically around half a liter. So that's like right here. Or if we looked here, like let's say this was, 1.2, or let's say, I don't know, let's not even, let's just say this distance, the difference here is 0.5 liters. So that is a typical quiet breathing. And again, you can think about a half a liter. In fact, maybe I should get a, right. If this is like about a half a liter here. Right, so every time, if I'm just sitting here quiet, actually sideways, right, about a half a liter of air comes down, comes out. That's my tidal breathing. This is about a normal tidal volume. So thing to remember is that there's that conducting zone. So of that 0.5 liters of air that comes down, some of it is just trapped in the dead space of your trachea and your bronchi. I remember we talked about the conducting zone versus the respiratory zone. So that conducting zone, which is basically dead space, is around 150 milliliters, 0.15 liters. So that means of this half a liter that you breathe down in your quiet breathing, only about, 350 mils is actually getting into the respiratory zone. Right? I mean, that's part of the reason why you're always mixing the stale air with the new air, right? When you blow out, not all of the air that is in there blows out. There's always the air that's trapped in this conducting zone, which is still stale air, and you're sucking in fresh air that mixes with that. That was why the partial pressure of the oxygen in the alveoli was appreciably less than the partial pressure of oxygen in the room. All right, so this is quiet breathing. This is when you are not trying voluntarily to increase or the amount you're breathing in or the amount you're breathing out. Obviously, we can do that intentionally. You can breathe in way more than a normal inhaler. Breathe out way more than a normal exhale. So let's look at those volumes and what they're called and how we measure them and typical values. So again, I'm going to kind of draw this picture of volume in liters. Let's let this be my quiet breathing. And like I said, that is going to be my V sub T, and it's around 0.5 liters. So if I just kept breathing like that quietly, that's what I'd be doing. If I inhale beyond a normal inhale, I can use my diaphragm can actually pull down 10 centimeters instead of 1 centimeter. And my scalene muscles and intercostal muscles pull and expand my rib cage. So you can really expand the volume of your thoracic cavity a lot beyond a normal inhale, which is going to expand your lungs. And you can suck in a lot more than a normal inhale. And this distance for this amount that I've just brought in here, it's the amount above a normal inhale. This is going to be my IRV, Inspiratory Reserve Volume. So when you're thinking about this, when you're drawing it on your actual graphs that you're going to have a little later in the lab, remember it's the amount you breathe in beyond a normal inhale. So you have to look at what is the normal inhale, and then it's the amount above a normal inhale. So that's the inspiratory reserve volume. Typically, it's around 3 liters. So usually you can suck in like 3 liters beyond a normal inhale. That's going to be the most you could breathe in. Then I'm back in quiet breathing. Obviously, I can breathe out beyond a normal exhale. So if I breathe out beyond a normal exhale, then I can go back into my quiet breathing here. This distance is my expiratory reserve. And again, it's measured from the amount you get. First, you get to a normal exhale, just a quiet exhale. And then it's the amount you can keep breathing out if you really push. And again, it's going to be from these intercostal muscles, abdominal muscles, anything you have to squish things. And a typical value for that is about a liter. Obviously, when you are blowing out every last little bit of air, there's still some air left in your lungs. You don't breathe out every last drop of air. There's actually quite a bit left. You don't deflate your alveoli until they're flattened. So the volume that is still, if this is 0 here, this volume that is the part you can't breathe out, that's always in there, that's called the residual volume. It tends to be. I'll tell you about how to find it in just a few moments. You can't measure it directly, right? IRV, tidal volume, expiratory reserve, you can actually measure using a spirometer. There's a way you can just see how much volume of air is entering or leaving the mouth. And you can actually measure ERV, IRV, tidal volume. Remember, this is tidal volume. This you can't measure directly. The residual volume, though, is what is used for like the Heimlich maneuver, right? If somebody is choking to death, and they have they can't blow out anymore. There's nothing left that they can do on their own to try to, create an airflow to dislodge the steak stuck in their throat or something. But there is air that is in the lungs still, and somebody can come up and manually compress their chest and increase the pressure in there and actually force some of this out. And that's what is creating that little air burst that the Heimlich maneuver uses to try to dislodge whatever's choking somebody. Like the Heimlich maneuver works because if you squeeze somebody's chest, there's actually still some air left there that you can get out, even though they can't do it themselves using their own muscular strength. Okay, we're getting close here now. So the total amount of exchangeable air, the most you can breathe in to the most you can breathe out, is called vital capacity. And that's just going to be the sum of all these things we just said. It's going to be the most you can breathe in, this inspiratory reserve, plus the tidal volume. Maybe you're here, you're blowing out, continue blowing out, and then continue blowing out beyond that. So this is my VC, my vital capacity. It's basically the sum of the IRV, the tidal volume, and the ERV. And obviously it's usually somewhere around 4.5 liters, right? If this is about 3 liters typically, this is about 1/2 liter typically, this is about 1 liter typically, this is around 4.5 liters typically. One of the things in the lab is going to be looking at data of a lot of people's measuring their vital capacity and trying to correlate it to different things. In general, the thing that correlates most reliably with vital capacity, does anybody have a sense? Anybody have any guess what kind of things might be correlated with somebody's vital capacity, the total kind of amount of air they can bring in and out of their lungs? You should have some guesses at least. I don't hear anything.
How big their chest measures?
Yeah, so your physical size, right? The in fact, one of the things we're going to look at in the data is height, people's height versus their vital capacity, and look to see if there's a relationship there. And it's like one of those spoiler alerts is people who are physically bigger, everything's a little bigger, including their lungs. So it's not going to be that shocking that their vital capacities are going to be larger if you are just physically like a bigger human animal.
Also, maybe like pathologies, like if they've had, like, I don't know, problems with their lungs or something.
So that can also have issues as well. So we'll talk about that. So and I should mention, so this, you should know all of this. In fact, we're gonna, part of the first part of the lab, part 1, is gonna actually have our subject just breathing into the machine and recording a graph that looks very much like this, and you have to annotate it, kind of like the way you annotated the EKG to make sure you understand the different parts. You'll have to annotate this spirogram and make sure you understand what is vital capacity, in relationship to ERV, IRV, tidal volume. If you are doing more clinical assessment, there's another version of vital capacity that is called forced vital capacity. That's, instead of just doing it more mathematically like we did here, forced vital capacity looks like this. So for forced vital capacity, this is again liters. You're breathing in and out and in and out. So this is my quiet breathing. And then you just in one go, breathe in as much as you can, breathe out as much as you can, and then just kind of go back. So this is my forced vital capacity. You're blowing out as fast as you can. Right? This is something that is typically the same as vital capacity. So if no pathology, is, similar to just regular VC. However, when people have these obstructive pulmonary conditions, like asthma, for instance, asthma where your air passages are constricted, then if you try blowing out really hard, there's a lot of resistance, and that pressure doesn't cause the same flow, and you can have less. It can be, this. So this is going to be, in fact, that's going to be part 2 of our lab, is going to be looking at forced vital capacity rather than just the kind of classic volumes. Like the part 1 is just going to be this kind of quiet breathing, inspiratory reserve, expiratory reserve, doing a mathematical combination to figure out the vital capacity. But then part 2 is going to be have the subject do this forced vital capacity. Have them just bring in as much air as they can and then blow it all out as fast as they can. And we can see what happens there. It's worth talking about the FEV1. So let me talk about that. In fact, let me draw this prettier again. So let's say this is my forced vital capacity. And I sucked in as much as I could. I blew out as much as I could. And this is obviously time on this axis. It's clinically important to know how much of this vital capacity can I actually get out in a reasonable amount of time. So we're going to talk about FEV1, which is the forced expiratory volume in 1 second. So this is how much of my lung capacity can I exhale in 1 second. So basically what you do is you look at the beginning of the forced vital capacity when they're starting to exhale, and you measure for 1 second. You say, all right, they started here, they made it to here. So this would be my FEV1. It's like, how many liters did I get out in 1 second? Right, you can, maybe I should draw. Right, so obviously this person here did not get it all out. In fact, this person still has maybe almost half of the air still after they've gone for 1 second, and that would be a bad thing. Typically, what you do is you look at the ratio. You look at the FEV1 divided by the total forced vital capacity. So right, so there's the total volume that they were actually ultimately able to exhale when they really try to just blow out every last bit of air. And then there is what proportion of that were they actually able to get out in the first second. So that's this ratio, FEV1 over FVC. So are there any questions about that? This is basically what percent of your forced vital capacity were you able to exhale in the first second? Right? If it was 100%, it would mean you actually got everything out in the first second, which is not kind of what happens. But typically, if somebody has healthy lungs, this should be somewhere between like 70 and 85%. Like this drawing I drew here, where this person actually had, I don't know, it looks somewhere around like, I don't know, 60% or something. That would be indicative of some kind of obstructive pulmonary disease, again, like asthma or something, where they're having a hard time. Even they generate the maximum pressure they can, but they are not getting that much of the air out in the first second. So in our lab, in part 2 of our lab, we are going to assess our subjects' FEV1 over FVC. And you need to make sure that you interpret it as well in the lab write-up, in the discussion. I mean, that's a big part of what we're doing with this lab, is kind of showing you kind of this typical way to assess pulmonary function. So are there questions about what exactly this ratio is? Okay. All right, so everything I've been talking about so far has been about the volume of the air in your lungs or coming out of your lungs. And I should mention while I'm still here, residual volume, you can't actually measure, like I said, because there's no way to actually have, by definition, you can't blow it out to be measured. But it's typically somewhere around a quarter of the vital capacity. Right, so it's typically somewhere around a little over a liter or so of air that is always in your lung that is impossible to get out of there. And like I said, that air is what's getting squeezed out during the Heimlich maneuver to try to push, dislodge whatever's going on. Okay. So now we're going to look at one last aspect of the air coming in and out. And rather than just the amount, we're going to talk about like how fast it's coming in, right? Because I can be breathing, sucking the air slowly, or right? Or I can like let it go out slowly, like, or, right? So the amount, the liters per second that air is coming in and out is going to be important. And that's going to be the flow. The liters per second of air coming in and out. And basically, if zero, what does that mean? If the flow is zero, what does that mean in terms of your current breathing?
I mean, wouldn't that be like you're not breathing?
Yeah, exactly. You're holding your breath, right? If the flow is zero, there's no air coming in or out. So I just kind of want you to get a sense of what we actually mean by flow here. The convention for the sign, if exhaling, you say you have a negative flow. If inhaling, it's positive. Right, so if I am blowing out like gently, it might be, -1 liters per second. If I'm really blowing out, it might be -5 liters per second. Right? Negative sign means it's out. The magnitude is like how much per second. Right? Same thing for positive. If I had +1 liters per second, maybe. If I had like +5 liters per second, I'm like trying to suck in as fast as I can. Right? So just kind of give you a sense. The sign tells you whether the air is coming in or out. The magnitude is telling you like how much per second. So in our system for measuring stuff that we use in the lab, it actually measures flow rather than volume. But you can calculate volume from flow very easily. Volume is just the integral of the flow with respect to time. If you haven't taken calculus yet, integral just means like kind of the summing up of adding together. Right, so if you have air coming in, you have some positive flow, it's going to just, the volume is going to be going up, right? As long as the flow is positive, you're inflating your lungs and the volume's increasing. If the flow is zero, then the volume just stays put wherever it's at because no air is coming in or out. If the flow is negative, meaning you're exhaling, that means the volume is going to be dropping because you're blowing air out of your lungs and you're deflating things. Right? So the relationship between volume and flow should feel kind of intuitive. If flow is positive, air is coming into your lungs, the volume's going up, you're inflating. If the flow is negative, you're exhaling, the volume's going down, you're deflating. If the flow is zero, the volume stays unchanged because no air is coming in or out, so the volume's not going to change. The actual little machine we use, it's kind of cool. So it's this thing that you can blow in. So you're basically breathing in and out. We always make sure we put a little nose clip on our subject because even if you don't think you're breathing through your nose, air is moving in and out of your nose. So you always have to put a nose clip if you really want to make sure that no air is escaping through the nose. So we're always going to use a nose clip when we do these experiments. We usually use a like a thing for a snorkel that kind of really fits into your mouth, so it really seals well. And there's a screen here that you're breathing through. So it's a screen, so air moves through it in and out, but it has some resistance, right? If air has to move through a screen, there's going to be some resistance. So the screen has resistance R. And then the computer has little pressure gauges that measure the pressure difference between the two sides here. We can measure the change in pressure. What's the pressure difference between the two sides of the screen as you're breathing in and out? So again, you're breathing in, you're breathing out, you're breathing out, you're breathing in. And the pressure is being measured across the two sides of the screen. And you know the formula. It's the same formula that we used for flow of blood. It's the same formula as we have for the flow of air. Basically, flow is going to be the pressure difference over the resistance. So because the resistance is known, it's just calibrated. The screen has a known resistance. The pressure is being measured by the computer sensors as you're breathing in and out. So it calculates flow and plots it on the screen for you. So that's how it's going to measure flow. And then it just does simple math. It just integrates the flow, and that gives you the volume. So on the screen, you'll see both the flow and the volume based on this whole system here. So let me show you what it looks like. So you're going to see both of these graphs on the computer screen when we're doing this lab. And you want to make sure you keep track that they're different because they'll look kind of sort of similar. But remember, volume is what we've been talking about in the beginning. This is what has the vital capacity, the ERV, the IRV. Flow is just the liters per minute coming in and out. So let me do this. I'm going to just to kind of put in a graph paper here so I can draw things that make sense. So if my flow is 0, the volume will just stay wherever it's at, right? As long as the flow is 0, the volume is not going up or down. It's going to stay. This is going to be time on. If my flow comes up, becomes positive, again, this is 0 here. As long as the flow is positive, what's going to be happening to the volume?
The volume will increase.
Exactly, the volume's increasing. At some point, I stop my inhale, my flow is back to 0. I'm going to hit some max here, but now it's just going to stay. As long as it stays at 0, this will now stay at this higher value. If I'm going to exhale, that means my flow is negative, which means this is going down. When I'm done with the exhale, this will now be back. So does this give you a sense of kind of the relationship here? when we're looking at the pulmonary function tests, you're going to want to look at both of these. And when we look at coughing, you're going to want to look at both of these and understand why they're different. Like this is telling you air is flowing out. This is telling you air is flowing in. Here we can see the volume is dropping while the air is flowing out. Here we see the volume is rising when the air is flowing in. What would it mean if I had something that looked like this? How is this different from this?
This app will change your life.
Heck.
So if you're a student or professional, you type a lot. And
Hold on
occasionally you might
trying to get my clock here. Okay. So what is different here in like 2 versus 1? Okay, start with a sign. Are the signs similar or different?
Similar?
Similar. They're both negative, right? They're both going down below 0. Right? If this is 0, anything below 0 is negative, anything above this is positive, this is negative. So these are both exhales. These are both exhales. What is different about them?
Number 2 is a lot deeper.
So deeper, be more
Larger.
with a much larger magnitude.
Yeah.
Right? So it's the liters per second that are leaving is much higher. So if I looked at the volume related to this, it's gonna be going down way farther and faster than I would have got for this more gentle exhale, right? I'm gonna have the volume dropping, but it's gonna be dropping much faster because I've got air leaving. The liters per second leaving are way more if I have a large negative magnitude of the flow. Does that kind of make sense? So, where this is going to come up, for instance, is when we're like part 3 of our lab is going to be looking at coughing, for instance. Like, how is a cough different from a normal exhale?
It's forced.
So one, it's forced. And what about in terms of like, we're talking about flow specifically. How do you think the flow of a cough is going to be different from the flow of just a quiet exhale?
The magnitude will be bigger.
Yeah, right. They're both exhales, but one is going to be a lot more air per second coming out. The air is going to be coming out way faster. Is way more
12 p.m.
air per second leaving than like a gentle exhale. Right. So when we're trying to understand what the heck is a cough, and we're going to ultimately be looking at volume and flow for the cough and seeing what happens. But I want you to just kind of get the sense of some kind of intuitive feel for what is flow. Like if the air's coming out really fast, that would be a large negative flow, like in a cough, for instance, or in a trying to blow out a candle. You need also a large negative flow compared to like a normal exhale. So, any questions about all of this? Okay. Let's see. We are now going to go to the lab itself. Let's see. Hold on a sec. Okay, so Spirometry Lab now exists here. So again, as always, there is the copy of the lab page. And it kind of just starts kind of talking about, this kind of shows a picture of what this kind of crazy setup looks like. Here's like our subject with the nose plug and blowing in and out of this thing with that fine mesh screen that is the resistance. The plastic tubes that transmit the pressure difference to the computer. And this is just kind of a prettier picture of what I was drawing. Tidal volume is going up and down and up and down. Inspiratory reserve is that value that is above a normal inhale to the most you can inhale. Expiratory reserve is the most you can exhale beyond a normal exhale. Vital capacity is the sum of all three of those, the total amount of exchangeable air. This residual volume down here, that's the amount of air that's always in your lungs that you can never blow out no matter how hard you try. So, this picture here from the lab manual is the same thing I've just been talking about. We're going to watch a little thing showing kind of how the setup goes, just so you can see how we get the data. But obviously in our lab, you don't have to actually set things up. And let me do a quick little aside. Even though we don't actually have to deal with this because we're not doing the lab itself in person, it's actually kind of trippy to think about that if you breathe in a liter of air, so let's say here's our subject, and they suck in 1 liter of air. And then they blow out the exact, in fact, so they suck in a certain amount of air, it's 1 liter that they suck in, and then they blow out that same air. Are they going to be blowing out 1 liter? If they blew out every single molecule and atom of air that they sucked in, what would be the volume that they're breathing out? Y'all remember your ideal gas laws? Remember, this is where you have to kind of go back to your, remember, PV equals nRT? This should look familiar. Right, this contains Boyle's law in it, right? We saw that volume was inversely related to pressure. That's why they were on the same side of this equation. That was how, pulmonary ventilation worked. But this has volume as being directly proportional to the temperature of the gas. So what do we know about the temperature of the exhaled air versus the inhaled air?
It's greater.
It's greater, right? We saw that. That was part of the lab last time, was the exhaled air is hotter than the air that was inhaled. So what does that tell us about the volume of the air you're exhaling here? If you exhale the exact same gas that you inhaled. What happens to the volume of a gas as you heat it up?
Increases.
It increases. They're directly related. Right? This should feel kind of familiar from chemistry. So That means if you suck in 1 liter of air and you blow out that same air, it's actually going to be greater than 1 liter, right? Because it is now increased in volume because the temperature went up. So that means if you look at, this is just volume, and you just watch someone breathe in and breathe out, it's going to start walking down. Every time you breathe out the same air you breathed in, it's actually a larger volume than you breathed in, right? If you breathed in 1 liter and you breathe out a little more than a liter, you breathe in a liter, you breathe out a little more than a liter, you breathe in a liter, you breathe out a little more than a liter. So you're always going to have this picture walking downward and going off the screen. So some of the stuff in the lab manual, which we're not going to be covering, is meant to try to adjust for this fact. So you get prettier pictures when you're looking at things. But does this make sense? Yes? No? Everybody's so quiet today. Okay. All right, so the first part is going to just be looking at lung volumes. I'll show you how that works in just a few moments. The second part are going to be the pulmonary function tests, where we actually do the forced vital capacity, and we can look for that FEV1 over FVC and stuff like that. And then the third part is going to be looking at coughing. And I'll talk a little more about that in a few moments when we get there. So, oh, and this, in case you're wondering what this is supposed to be, that's coughing. It's supposed to be a cat getting rid of a hairball. So, okay, so this first video here, we're not going to show in like right now because it's everything I just talked about. But, you know, on your own, you can watch this. This is somebody else basically saying the same things I was saying. So it's always a it's always good to see somebody else say the same thing, because sometimes it helps you see it in a slightly different way. They also talk about some other volumes that you don't care about. So if you're watching this little video here, you know, only pay attention to the volumes that I've already talked about. You know, ERV, IRV, tidal volume, but they also go over some other stuff that you don't need to know. So don't stress about the volumes that they talk about that we did not cover. All right, so I'm going to do here, this is just going to be, what's the time? Yeah, we got the time. We're going to, for 7.5 minutes, we are going to watch what it actually looks like when you do this. You don't have to actually write down the values right now, but you are going to need these values for your write-up. So you can either write them down as we're going through this now, or you can go back and look at this. But part of this lab is basically just getting the basic measurements for IRV, ERV, tidal volume, seeing how you measure them and getting some actual values. You know, the values that we're going to measure are not necessarily real, because we didn't actually bother to really calibrate the system really well. So, but they're ballpark. They're ballpark fine. All right, so let's do this. This is another one where I found some cool graphics to do the title page. Okay, here we go. All right, so here we're going settings, spirometry. Right, so this is the same system we were using to measure the EKG, but now instead of measuring the voltages across your skin, the system is going to be doing kind of these calculations based on the pressures and graphing the flows and volumes coming out of your mouth. And here on the top, we've got the, come into focus, is the flow rate. So with positive flow, meaning air is being sucked into your subject, and negative flow, meaning that air is blowing out of your subject. And below is the integration of flow, which is the volume in liters, which we will see increasing as the lungs inflate, and we'll see decreasing as the lungs deflate. Here we have our subject. This is the mouthpiece hooked up to the little filter. This filter is the only disposable part of the system. At the end, we'll throw away the filter, but all the rest will be sterilized and reused. And this is the part that actually has the little screen in it with little hoses that go up to the spirometry pod to detect pressure differences so you can calculate the actual flow of air. Tubes facing upwards so any condensation does not pour down into the system. So now, while this is staying completely still and the system's warmed up, we now have to zero the system. So zero flow will be zero volume change. So here we go up into spirometry pod. Again, you're not going to have to do this, obviously. Clicking on 0. And that should bring this line up to 0, saying no flow if no breathing in. And then if we click on start, we can double check that the volume stays relatively constant if there is no breath coming in or out of the system. Right, so that's because the mathematics of integrating flow to get the volume. You need to make sure that the system knows what does it look like when there's absolutely no flow. It's just sitting on the table. So then it knows, okay, that's what zero flow means. And that means the volume doesn't move because there's no flow. And so we are good to go for the next step. First, we'll put on the nose clips. Make sure that all the breath coming in and out is through the mouth. Obviously, it's a little awkward. It takes a little while to start breathing normally. As we have our subject, we're going to see our subject breathe in strongly, and we'll see what happens to the direction it's going up, and have her breathe out, blow outward. We see the volume goes down. That is what we want to see. And so now, as she continues breathing, notice that there's a lot more dead space because of this tube. So you'll probably have to breathe deeper to actually feel like you're properly ventilating. And here we just see the top, which is as she breathes in, the flow is going positive. When she breathes out, she holds your breath for a moment. And there's zero flow, meaning that there's no air coming in or out. Breathe in, or that's breathing out, and breathing in goes up and down. So looking good. So at this point, let's stop again. All right, so here we're gonna have our subject just breathe easy. And if we go look here, we can just see the volume goes down as she breathes out, comes back up as she breathes in, out, and in. And now we're going to have our subject do an inspiratory reserve. So she's going to, on her next inhale, she'll just breathe in as much as she possibly can. There we see all that extra volume in, and now she's going to breathe out and go back to her quiet breathing, her tidal breathing. Good job. Right, so everybody sees the inspiratory reserve. She's normal, quiet breathing, breathing up to where the normal inhale is. That's still just the top of a normal inhale. And then everything above that is going to be the inspiratory reserve. We have PDFs of these graphs that you can then print out, and you're going to have to kind of annotate them and draw on them so you can clearly show that, where is the inspiratory reserve, where is the tidal volume. And then we also saw another function of the respiratory system, which is vocalization. All right, so now we still see our subject doing the quiet breathing. What she's going to do now on her next exhale, she's going to continue past the normal exhale till it's all out, the expiratory reserve. Oh, there she goes. And now she's back to normal breathing there. You can see an expiratory reserve is typically not as much as an inspiratory reserve, but we see that it's down lower than a normal. So this is looking good. Let's give this a pause. All right, let's just go from the trough to the peak of just a quiet breath, and we look at the volume here. You can see. Remember the marker function we used last time to look at the timing difference in the the PR interval. You can also use the marker to look at the volume difference between different parts of the graph. So that's what we're using, this little marker. It says about 0.73 liters. Right, so that's from the little marker to the cursor. So again, that's a tidal volume, the trough to the peak of just a quiet breath, in to out. And it typically, when you're breathing in that big long tube, because the dead space is much larger, remember I said 150 mils of dead space normally, now the dead space is like twice as much because she's got the whole big additional elongation. So that means there's even more stale air she's mixing with the fresh air. So she's going to have to take deeper breaths to actually feel like she's got enough oxygen, fresh air coming in. Our computer operator here is going to put the marker at the top of a normal inhale, but now fly her cursor up to the... Right, see remember when you're doing IRV, inspiratory reserve, it's the top of a normal inhale up to the maximum that they could inhale beyond that. So this distance from where the marker is to where the cursor is, that's going to be that volume, and then we'll look over and it'll say what that actual value is for this subject right now. Top of the inspiratory reserve, and we can see that it is about 1.4 liters of volume above a normal inhale. And now our operator is going to take the marker and put it right at the bottom of the exhale. We're going to just do it there even. And then go to the bottom of the expiratory reserve. Right. Again, here's the bottom of a normal exhale. This is the bottom of when she was really blowing out the rest that was left beyond that. And that's going to be expiratory reserve. And again, don't worry too much about the values because we never really calibrated the system to make these, so this is all kind of ballpark. And we can look the volume again. Here we see it's about 0.2 liters. Right, so in your write-up, use these numbers that we're getting here, but don't get too caught up in saying, oh, Becky must be have some disease because her values are so low. Note that we did not actually calibrate this system, so these volumes are not necessarily accurate. They are just representative. Okay, so there we have all of her main breath volumes. For her vital capacity, it would just be a sum of all three of those. All right, so that's going to be part one, is just getting familiar with what are those volumes. And then it says here, print out and glue in your notebook, BB, that's Becky Brown, Spirometry Part 1 PDF. It's just that printout of what you just saw, and then annotate it. On this, you're going to draw and you're on the actual thing that you print out the where is tidal volume and put in the measured value. Where is the inspiratory reserve from where to where and what's the value? Where's expiratory reserve? So that's part one of this lab, is just doing that. Any questions about what that means? Okay. The next part is the pulmonary function test. So like I said, this is going to have your subject do the forced vital capacity, and then this system actually will automatically calculate all sorts of cool stuff for you. So you'll see how that works right now. All right, so now our subject is going to do some quiet breaths and then go into a forced vital capacity. So, and point the thing away from the operator, please. All right, here we go. Right, so it's kind of hard to see, but she sucked in as much as she can. She's kind of arching over, bending to try to just compress her thorax as much as possible, get every last bit of air out. So what she's doing here is she sucked in as much as she could, and then she blew out every last bit of air within her lungs. Back into some quiet breathing. And if we take a look at the volumes here on the screen, we see a beautiful pattern of the tidal breaths followed by an inspiratory reserve, directly followed by the expiratory reserve back into quiet breathing. So we can now pause this. Right, and so you see that quiet breathing leading up, and inspiratory reserve, and then immediately blow out every last bit she could. Expiratory reserve bottoms out, and then just kind of back into quiet breathing. So the machine is going to look specifically what's going on here and analyze it in a way you'll see in just right now. And select some in leading breaths and outgoing breaths, and then that's perfect. Now we are going to go into. Oh, and actually, it's worth looking up here briefly. Notice what was happening during that inspiratory reserve when she's sucking in as hard as she can. Look at the flow compared to a normal inhale. It's still a positive, it's still up, but it's a much larger value positive because she's sucking in really fast. That expiratory reserve, this is the flow when she's really blowing out as hard as she can. It's negative like a normal exhale, but it's a much larger negative number. So the system is actually going to give you the values, even the peak inspiratory flow, the peak expiratory flow. What was the value of the flow at when she was sucking in as hard as she could or blowing out as hard as she could? Go into the data window. And there we have this beautiful picture here, which you will have access to.
To print.
Yeah, so we're going to print this, and the values we'll be able to get off of the report, which we will. Right, so here, I'm just saying, so you're going to be printing this out. We also have the data report for you, which you can use to get the actual numerical values that you need to kind of annotate this. And again, you're going to calculate the FEV1 over FVC and make sure you talk about the significance, why we care. We'll get in just a moment. In fact, it's worth, if we go. So right here, you can see this here, this is in 1 second. This is how much of her exhale came out in 1 second. This kind of inside line, FEV1. That bigger value, this is the total forced vital capacity from the most you could breathe into the most you could breathe out. This of that total amount, this amount was 1 second. So that's going to be important.
To print.
Yeah, so off of the report, this is showing the peak inspiratory flow and peak expiratory flow, as well as the volumes, her forced vital capacity and forced expiratory volume in 1 second on the bottom.
Okay, so next report.
Now the report. And this we will also have for you. This is the actual values which you can use to add to that previous graph. So you actually have numerical values. Right, so you don't have to print this out, but you should look at it and use the values to annotate the other drawing. You know, basically peak inspiratory flow, when she was sucking in as hard as she could, it was 2.5 liters per second. Peak expiratory flow, 3.6 liters per second. Forced vital capacity, 2.14 liters. FEV1 was 1.55 liters. FEV1 over FVC, that's that kind of number we care about. That ratio, 72%, which is kind of low, but still like okay. Average VT, that's just average tidal volume, was about 0.7 liters. Frequency was about 19.7 breaths per minute. That's what these other things are. And again, there's PDFs. So there is the PDF of the actual forced vital capacity that's been annotated, that you are then going to further annotate with numbers and talk a little more about. And again, we've also given you the data report that has the values that you can use to annotate this thing. So, are there any questions about that part of the lab? Again, this is a typical way to assess for like kind of obstructive pulmonary problems. In particular, like if you don't have problems, you can get, you know, usually about 80% of your vital capacity out within the first second. And if it's appreciably lower, you know, we have people with asthma or something, and it's like around 50% or something. All right, so the last part is coughing. I'll just show this to you and then I'll talk about it a little bit, because we still have a minute, so we're good. All right, so now our subject is going to do some quiet breathing, and then she is going to cough, and just like a cough, like there's something got to get out. She's breathing. Oh, just one cough, one cough. Let's do one cough. All right, now let's take a look. All right, so this is nice. This is really nice. We can see on the top the flow. When the cough is happening, we see a very high outward flow. Those, right, you all see that? Like a normal exhale, these little dips down are the normal exhales. When she does that cough, it's a much larger negative number. It's this sharp, strong outward flow. That's what I was talking about a little earlier. When a cough isn't just air coming out, it's coming out really fast. Those spikes going downward, that is saying there's a high flow rate of air out of our subject. If you look at the volume change, right, so we can I'll ask you, does the amount, we say the the speed that the air is coming out is much faster. We can see from that flow graph. Is the actual amount of air coming out during a cough very different from a normal exhale? Take a look at the screen. Look, compare the change in volume. Maybe. Again, here is the cough. We can see the flow, the speed that it's coming out is really fast. But then we look at the actual volume of air that left her lungs when she coughed. Is the volume very different from a normal exhale?
No.
No, not at all. It's pretty much the same as a normal tidal volume. Do you all see that? So this is one of these things that's kind of non-intuitive, maybe. Like a cough, it's a very fast, explosive movement of air, but the actual amount of air is no different from a normal exhale. Even though it looked dramatic, right? she wasn't like holding back. That was kind of a dramatic cough, and there was a dramatic increase in outward flow, but the amount of air was not that different from a normal exhale. Like, why would that be useful? Why do you think that makes sense, actually? I think if there's, yeah, I mean, you can finish watching this. It doesn't really, it kind of just continues, just kind of describing what I'm talking about. Why is that probably useful? Why does it make sense that you don't have a huge amount of air coming out as well as it coming out fast? Well, let's say I'm like eating something and it's like, oh, and I try to dislodge it because it's stuck in my throat. What if it didn't? What if that first cough didn't work? Didn't knock it out and I'm still choking? What can I do?
You can keep coughing.
I can keep coughing. If I like blew my wad and just coughed out all my air in that first cough, there'd be nothing left. I wouldn't have any more coughs left in me, right? If I have this explosive blast, but it's not such a large volume, it means I can let I've got a few of them in me that I can use to try to dislodge this thing and hopefully survive this choking incident. Right? Does that make sense? Right? You don't just get rid of your whole expiratory reserve. You hold on to your expiratory reserve, so you got some reserve. So you got some air left for the next cough if you need it. So like when you're looking at this coughing data and writing up your coughing data, definitely think about explicitly the difference between the flow during a cough versus the volume during a cough. That's kind of an important take-home message for this part of the lab, right? And if you like in the module, there's just a nice little where is it? File preview. Here you go. Here is that little printout. It shows both the flow and the volume. Make sure in your write-up, you kind of show where the cough happened and how you know, and talk about its characteristics. So any comments or questions about that? Right, it's pretty, this lab is pretty straightforward. It's the first part is just lung volumes, making sure you can identify and you understand what they are on a real spirogram here. The second part, the pulmonary function test, is seeing this forced vital capacity, and in particular, making sure you understand that FEV1 over FVC. And the last part is, kind of the anatomy of a cough and really understanding what a cough is and, the flow versus the volume. All right, so any comments, questions, or anything before we let that go? All right, so that's it for today.